Welcome! Ironically, we'll start our course on quantum cryptography with a rather classical concept. We will see how to use a classical encryption key to encrypt classical information. What does it mean to encrypt information, and why do we want to do this in the first place? Let's imagine that we have our two parties, Alice and Bob. We will be concerned quite a lot with the private lives on Alice and Bob. This time, Alice would like to send a message, M, to Bob. For some reason, Alice and Bob have a lot of secrets. Alice does not just want to send the message to Bob, because she's very afraid that an eavesdropper, Eve, is trying to intercept the message and read it. Throughout this class, we will assume that the eavesdropper is all-powerful. The eavesdropper, or Eve, has a quantum computer in her basement with an arbitrarily large quantum memory. She is extremely smart, and most importantly, she is spending all her efforts on only one thing, namely trying to read the secret messages between Alice and Bob. How can Alice and Bob protect their messages? Let's suppose that Alice and Bob already share a key, an encryption key, K, and they want to use an encryption scheme. So this means that to encrypt, Alice applies some encryption function, enc, to her message and the key. The resulting encrypted text, the ciphertext, E, she sends to Bob. To read the message, Bob has to decrypt. He applies a function, dec, to the ciphertext E and the key K to get back the message. So enc and dec together form an encryption scheme. What properties should such a scheme have? First, we want the scheme to be correct. Bob should be able to read the message. Second, we want the scheme to be secure. Eve gains no information about the message M if she doesn't know the key. So the message M is independent of the ciphertext E. We will see later what precisely this means in the quantum world. Eve doesn't know the key. For the moment, let's just say that classically, Eve is independent of the key and the key is uniform. Meaning that the probability from Eve's perspective for the key taking a certain value K is 1 over 2 to the n. I assume that the key has n bits. No. A very simple encryption scheme is known as the one-time pad, and it works like this. Alice's message M as well as the key K consist of n bits. The encryption function enc now works as follows. For every bit in her message, Alice computes the XOR with the key bit. So she takes M1 and she XORs it with K1 to obtain an encrypted bit E1. The XOR is nothing else than the sum mod 2 of these two bits. So to be precise, the XOR is the same as the sum mod 2 of the 2 bits. So Alice sends the encrypted data to Bob. How does Bob decrypt? What is his decryption function? DEC. Bob, who does have the key, the same key as Alice, takes every bit of the encrypted message and XORs it with the corresponding bit of the key. Observe that if I XOR any bit with itself, I get 0. So what this means is that if Bob adds the bit K, remembering that E1 is itself just M1 XOR K1, we get back the message. So our encryption scheme is correct, in the sense that if Alice and Bob have the same key, then in fact Bob can recover Alice's message. So why is this scheme secure? In the sense that Eve does not gain any information about the message. I will analyze this purely classically. And let's recall the demand for security, which is also known as Shannon secrecy. It essentially says that the probability Eve assigns to a message, M, is independent of having seen a particular instance of the ciphertext, E. Note that this is equivalent to saying that the ciphertext E is independent of the message. So to see this, note that I can write the joint probability of the message and E as the probability of the message times the probability of E given the message, or I could write it as the probability of E and then the probability of the message given E. So asking that these two things are the same, I might as well ask whether these are the same. So if these two here are the same, then also these will be the same. So how can we see this? It does, of course, crucially rely on Eve not knowing the key. That is, all keys are equally likely for her. So I will do this calculation, assuming for the moment that we just want to encrypt one bit. Our message has length 1, and we will use 1 bit of key. But you may check that the argument is precisely the same for longer messages. If you think about a message bit, M, having a certain value, with probability half, the key bit that I'm going to add to the message, and I'll omit the index here because n is 1. So with probability half, we will compute, so probability half, k is 0, and we will compute encrypted bit M XOR 0, which is M. With probability half, the key bit will be 1. And in this case, the encrypted bit will be the message bit flipped. So you can see that no matter what message we start with, the probability that the encrypted bit is equal to the message bit is half, and that it's equal to the message bit flipped is also half. We thus see that the probability of the encrypted bit in both cases, taking the value m, is half, and taking the value not m is also half. So we see that the encrypted bit, the probability of the encrypted bit taking on a particular value is in fact a half. we could do this computation for any message that we start with. So we see that the encrypted bit is independent of the message. And I'll write out this calculation in full detail in the lecture notes. So we see that our scheme is secure. Eve cannot gain any information about the message from something like the ciphertext that is independent of the message. Of course, you can now wonder, where do these keys come from? For the one-time pad, we use the key as long as the message. Our security calculation crucially depended on this. Is there a scheme that could also be perfectly secure, but use a smaller key? As Claude Shannon here discovered a long time ago now, the answer is no. In order to be perfectly secure, we need a key that is as long as the message. This means that if Alice and Bob already have a few gigabytes of key and they use it to send a video from Alice to Bob, after the video arrives, they essentially run out of key. There is no way for them to send another video if they don't have any key bits left. Keys are thus an important resource. By using classical communication, it is impossible for Alice and Bob to produce new keys if they can just communicate over an open communication channel that Eve can listen to. This is the case even if they start with a little bit of key to begin with. The cool thing is that we will later see that with quantum key distribution, we can extend the amount of key. Alice and Bob can take a gigabyte of key and turn it into an arbitrarily long, possibly infinitely long encryption key to keep communicating securely.